Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had completed our discussion on the ground model, ground reflection model for wireless signal propagation. We said in the ground reflection model, I have a total received signal field strength which is given as a sum of the line of sight or the direct component plus the reflected component ER. Further, we said that in this ground reflection component, the received field strength is proportional to 1 over d square. Hence, the total received power is proportional to 1 over d to the power of 4, that is the power decays as the fourth power of distance. Hence, the path loss exponent is nothing but 4. Hence, the received power in dB is P tilde, the reference, minus 40 log d over d tilde, that is, this is a path loss exponent of 4. Hence, there is a path loss of 40 dB per 40 dB. Hence, there is a loss of this thing, it decays as 40. Okay. And essentially, the other thing that we started looking at is we started looking at the Okumura model for wireless communication. We said that in a practical scenario, that is in a practical wireless channel propagation scenario, we want to consider a model which gives us signal strength as a function of distance, and this Okumura model is one such practical model which is applicable in practical scenarios, that is to accurately model the received signal strength as a function of the distance. And we said that in the Okumura model, the 50th percentile path loss, that is L50 in dB, is given as LF, the free space path loss, plus A mu, which is a correction factor which is a function of the carrier frequency and the distance, minus GH, which is a gain factor, that is where you are subtracting from the loss. This gain is arising because of the height of the transmit antenna. Another gain which is arising because of the height of the receive antenna, minus G area, which is essentially the area gain factor, that is, as you move from an urban to a suburban to open area, there is less clutter, which means there is a net reduction in the loss. Hence, there is a gain factor which subtracts from the 50th percentile path loss. All right. And we said we looked at the different expressions. We looked at the expressions for the free space path loss. We looked at the expressions for the transmit and receive antenna height gain factors, and then we also looked at the charts which give us this A mu correction factor, and then we also looked at this G chart which gives us the G area factor, and then we started looking at a comprehensive example. We wanted to use the Okumura model to characterize the median path loss at a distance of 8 kilometers when the carrier frequency Fc is 2.1 gigahertz, HTE is 40 meters, HRE receive antenna height is 2 meters, and we are considering a large city environment. That is, we want to look at this example in a large city environment to essentially consider what is the received signal strength as a function of the distance. And as part of it, we had looked at the free space loss. We said the free space loss is 117 dB, the transmit antenna height is minus the transmit antenna height gain factor because of its height 40 meters is minus 14 dB, and let us start from this point and continue with this lecture. So, we want to next thing we want to compute is the receive antenna gain factor. We have the receive antenna gain height equals 2 meters, hence the receive antenna gain factor G H R E equals 10 log 10 2 by 3 equals minus 1.76 dB. All right. So, the receive antenna gain factor, that is minus 1.76 dB, corresponding to a height of receive antenna height of 2 meters. all right. So, let us now look at the next factor, which is essentially want to compute the A mu factor, that is the correction factor. Let us look at we said that the cell radius equals eight kilometers. Hence, we want to compute the A mu factor at 2.1 gigahertz and 8 kilometers. For that purpose, we have to look at the chart related to the Okumura model. Let us go and look at the chart that is related to the Okumura model. At 2.1 gigahertz, if you look at 2.1 gigahertz and I approximate the distance of 8 kilometers, I am approximating this by So, I go to this chart for the A mu correction factor and I look at the carrier frequency corresponding to 2.1 gigahertz. I am approximating, since I do not have any curve for 8 kilometers, I am approximating using the curve for 10 kilometers, and hence I look at on the 10 kilometer curve, I look at approximately 2.1 gigahertz and I see that factor A mu f d is essentially 34, it is roughly approximately 34 dB. Hence, what we can say is, if we look at this, if we go back to this A mu factor corresponding to 2.1 gigahertz and 8 kilometers from the Okumura model, that is approximately equal to 34 dB. So, this A mu factor corresponding to 2.1 gigahertz and 8 kilometers, that is equal to 34 dB. Hence, essentially one can put all these things together. Hence, putting all these things together, further, since the environment is urban, remember we are considering an urban environment, that is a large city environment. Hence, the G area factor, that is 0, because the G area factor is only positive only for suburban or open and quasi open areas, that is, since we are considering an urban environment, the G area factor is 0. Since the environment is urban, the G area factor is 0. Since the environment is urban, the G area factor is 0. Hence, we have now all the components that we need to put together to compute the path loss, the 50th percentile path loss. The 50th percentile path loss in the Okumura model, L50 in dB is nothing but the free space path loss plus the A mu factor f of d minus G h T E minus G h R E plus G minus G area. This is nothing but the free space path loss, which is 117 dB, minus plus A mu, which is essentially 34 dB, minus the transmit antenna gain factor, which is minus of 14 dB, minus 1.76 dB, and that you can put together, that is approximately equal to 167 dB. Hence, we have computed the Okumura path loss for the Okumura model, corresponding to the model at 2.1 carrier frequency 2.1 gigahertz and 8 kilometers in a large city for a transmit antenna at 40 meters and receive antenna at 2 meters, and we found out that the path loss in practical scenario is given by 167 dB. That is what the path loss that we get from the Okumura model. Hence, this shows us in practical scenarios to essentially reach the receiver or the mobile user at a distance of 8 kilometers, you have to essentially account for this path loss. So, the transmit power has to transmit high enough power, so that after the path loss is removed, you have enough power remaining for the decoding at the receiver. Alright. So, this path loss has to be accounted. So, the transmit power has to be essentially increased to compensate for this path loss. That is the help, or that is essentially the purpose of all these path loss model. And there is another popular path loss model which we will also discuss, and which is also again relevant for practical scenarios, and this model is known as the Hata model. This is the Hata model for propagation, and the Hata model is another popular model for signal strength prediction. So, this is the Hata model. The Hata model is another popular model for signal strength prediction, especially in cellular scenarios. So, this Hata model, similar to the Okumura model, this Hata model can also be employed for essentially signal strength prediction in cellular scenarios. And the essential reason or the essential motivation for the Hata model is that it presents an analytical formulation for the graphical models or for the plots and so on, the graphical information that is embodied in the Hata model. That is, remember, in the Okumura model, we look at a lot of these plots to derive the A mu factor and the G area factor and so on. Those have now been essentially simplified into analytical expressions, so that one can compute the received path loss without the received path loss at a certain distance without the aid of some of those plots, and that is essentially the advantage of the Hata model. So, the Hata model essentially it provides an analytical formulation for the graphical information that is given by the Okumura model. So, the Hata model presents an approximate analytical formulation for the graphical information provided by the Okumura model. Okay, so what is the Hata model? The Hata model essentially is an analytical approximation of the Okumura model. Alright, that is what the Hata model is. And employing the Hata model, the median path loss, the expression for median path loss for urban areas in the Hata model is given as follows. The Hata model median path loss for urban areas is given as the median path loss, again similar to what we had in the Okumura model. The median path loss L50 dB is 69.55 plus 26.16 log 10 carrier frequency in megahertz minus A H R E, I am going to describe these terms shortly, plus 44 plus another factor which is essentially minus 13.82 log 10 HTE plus another factor which is essentially 44.9 minus 6.55 log 10 HTE, where HT is the transmit antenna height, into log 10 distance in kilometers. Okay. So, this is the expression for the Okumura model. So, Okumura model gives the 50th percentile path loss using this expression. Let me define the different quantities here. L50 dB equals the 50th percentile or the median So, L50 similar to what we had seen earlier is the 50th percentile path loss or the median path loss in dB. So, this is the 50th percentile or median path loss in dB. FC megahertz is nothing but the carrier frequency, but it has to be given in megahertz. This is equal to the carrier frequency in megahertz. Fc equals the carrier frequency in megahertz. HTE equals the transmit antenna, HT equals the transmit antenna height, HRE equals the receive antenna height, and AHRE is the mobile antenna correction factor. The factor AHRE, the factor AHRE is nothing but the mobile antenna correction factor. D kilometers is nothing but that is the distance in kilometers. The distance d is the distance, however d kilometers is the distance, it has to be given in kilometers, that is so this distance has to be given in kilometers, and the transmit and receive antenna heights are constrained as follows. The HATA model HTE, HRE, the transmit and receive antenna heights are constrained as follows. The HATA model transmit and receive antenna heights are the transmit and receive antenna heights in the HATA model are constrained as follows. We have 30 meters less than HTE less than 200 meters and 1 meter less than HRE less than 10 meters. So, the transmit and receive antenna heights are constrained to lie between 30 and 200 meters. The transmit antenna height is constrained to lie between 30 and 200 meters, and the receive antenna height is constrained to lie between 1 and 10 meters. These are the range of the different heights in the HATA model. Okay. So, let us again and let us now look at the correction factors. Remember, we talked about this HRE, which is the mobile correction factor, and that is given as follows. So, let us look at the mobile antenna. The mobile antenna correction factor, that is nothing but AHRE, and that is two different expressions for a small to medium city and then for a large city. So, for a small to medium sized city, HRE is given as 1.1 log 10 FC minus 0.7 into HRE minus 1.56 log 10 FC minus 0.8 dB. That is, this is the expression for the mobile antenna correction factor for a small to medium sized city, that is 1.1 log 10 FC minus 0.7 whole into HRE minus 1.56 log 10 FC minus 0.8 dB. And for a large city, these correction factors are given as follows, that is AHRE. Again here we have two expressions for a large city. One is 8.29 into log 10 1.54 HRE whole square minus 1.1 dB if FC less than or equal to 300 megahertz, and it can be 3.2, it is 3.2 log 10 11.75 HRE whole square minus 4.97 dB if Fc is greater than or equal to 300 megahertz. All right. So, this antenna correction factor for a large city is equal to 8.29 log 10 log to the base 10 1.54 HRE whole square minus 1.1 dB if Fc is less than or equal to 300 megahertz. It is equal to 3.2 log 10 11.75 HRE whole square minus 4.97 dB if Fc is greater than or equal to 300 megahertz. Okay. So, this is essentially in essence the Hata model which can essentially employ to characterize the path loss in an urban environment. Again, similar to the Okumura model, we can look at an example for this Hata model. Let us look at the same example that we have considered previously, which is essentially employing the Hata model compute the median loss at distance 8 kilometers when the carrier frequency Fc equals 2.1 gigahertz and HTE equals 40 meters and HRE equals 2 meters. That is, we are trying to again compute a similar thing, that is, we are trying to consider a cell radius of 8 kilometers, and when the carrier frequency is 2.1 gigahertz and the transmitter height is 40 meters and the receiver height is 2 meters, we are again trying to compute the received signal strength at the cell edge, but using the Hata model. All right. So, that is what we are trying to use. So, using the Hata model, first we have to convert the frequency into megahertz. So, Fc in megahertz is equal to 2.1 gigahertz divided by 10 power 6, that is nothing but 2.1 into 10 power 9 divided by 10 power 6, that is nothing but 2100. So, the frequency in megahertz is 2100 megahertz and the distance in kilometer is 8 kilometers and the distance in kilometers is 8. We have the mobile antenna correction factor, and going back to this expression for the correction factor, we know that the carrier frequency is 2.1 gigahertz greater than 300 megahertz. Hence, we use, also it is given that it is a large city, hence we use 3.2 log 10 11.75 HRE square. So, let me compute here, let me write here that it is a large city. For a large city, hence the mobile antenna correction factor is nothing but 3.2 log 10 11.75 into HRE, which is 2 whole square minus 4.97 dB, which is essentially equal to 1.04 dB. Hence, the mobile antenna correction factor is 1.04 dB. Hence, we have the 50th percentile path loss in the Hata model L50 equals 50th percentile path loss from the Hata model that is equal to 69.55 plus 26.16 log 10 to the base 2100, that is the carrier frequency in megahertz, minus 13.82 into log 10 to the base 2 minus our mobile antenna correction factor, which is 1.04 plus 44.9 minus 6.55 log 10 to the base 40 into log 10 log 8 to the base 10, where 8 is nothing but the distance in kilometers. So, this is essentially the net expression, and these different values can be simplified as follows. You can check these. This is essentially 86.9 dB. This is essentially 22.14 dB. This is minus 1.4 and this is essentially 31.07 dB. Hence, the net 50th percentile path loss is 69.55 plus 86.90 minus 22.14 minus 1.04 plus 31.07, which is essentially 164.34 dB. Hence, the L50 employing, this is nothing but the 50th percentile path loss employing the Hata model. Fiftieth percentile path loss employing Hata model is 164.34 dB. If you remember, if you go back to the path loss employing Okumura model, that is about 167 dB, and now we are saying in the Hata model, that is about 164 dB. Hence, these values are approximately close, about a difference of a dB or 2, that is 167, this is about 164 dB. Hence, the Hata model and Okumura model essentially received in the same signal strength predictions. All right. So, these can essentially be used, but the advantage of the Hata model now is essentially that the Hata model does not need the use of any graphical information like the plots that were used in the Okumura model. By using these expressions, one can succinctly or comprehensively essentially characterize the path loss at a given distance, which, as I said, is again very informative or very helpful, especially in cellular scenarios when you need to characterize the received signal strength at the edge of the cell to account for the transmit power that has to be, or the additional transmit power that has to be transmitted to account for the path loss for transmission to the cell edge users. Let us now consider the log normal shadowing, that is the other aspect of a wireless communication system, which is the log normal Let us now consider the log normal shadowing. in a cellular environment, apart from path loss, there can be other obstructions to the signal, for instance like large walls, large buildings, and the user if is occasionally behind these large obstructions, their received signal strength can be severely lower. So, apart from the path loss that exists in the cellular environment and signal environments, there is additional random factors depending on the surrounding clutter environment which cause additional loss. Hence, the received signal strength, if you look at any place or any place at any distance in an environment, is a random variable, because it depends from place to place on the clutter environment, and it also in fact depends on time to time, because the clutter environment such as vehicles and so on are mobile. Hence, this clutter environment is essentially a random variable, and this hence because of this clutter environment or because of this different scattering environment, the received path the path losses at the same distance vary versus different places, and they also vary as a function of time. Hence, this path loss at any particular instant is actually a random variable characterized by the 50th percentile or the mean path loss that we had derived earlier. All right. So, the surrounding scatter environment at any instant at any place, the surrounding scatter environment at two different locations or at different locations may be very different in a wireless scenario, or is very different in wireless. So, the scatter environment is very different in a wireless scenario. For instance, a user can be shadowed by a large object such as walls or buildings. For example, users can be shadowed by large objects So, users can be shadowed by large objects such as either walls or buildings. Hence, the received signal strength is actually a random variable, because depending on the random clutter or scatter environment, the received signal strength is actually a random variable. Thus, the net received signal strength is basically, so thus the net received signal strength, the net received signal strength is basically a random variable with the mean predicted by the path loss. Hence, the received signal strength is essentially a random variable with its mean predicted by the path loss. Remember, we defined the 50th percentile received signal strength, and we said 50% of the time the received signal strength is greater than this L50 and 50% of the time it is lower than this L50. That is essentially saying that this is a random variable, depends on the scatter environment. The 50th percentile value is given by the L50 from the Okamura or Hata model, and the rest is essentially a random, and then it is a deviation, a random deviation about this 50th percentile. Hence, if you look at the net, the random dB deviation can be modeled, and it is modeled as a Gaussian with a certain variance. This random dB deviation about the mean received signal strength, this random dB deviation about the mean, about the mean signal strength can be modeled as a Gaussian RV that is x sigma, such that it is Gaussian with 0 mean and variance sigma square. What we are saying is basically this, that this random deviation, this deviation can be modeled by Gaussian random variable with 0 mean and variance sigma square. What you are saying is as follows, that is, if I look at my path loss, my median path loss or my mean path loss is something that looks like this, and then I have a random variation about this mean. So, this is the mean or the median, this is median path loss, and then there is a deviation about this with a spread. This is the spread, which is nothing but sigma. Hence, for instance, the path loss can take any values in the range. For instance, if you ask what is the probability that the path loss lies here, that is essentially given by the probability that the path loss essentially lies in this small region. So, the path loss we are saying can fluctuate as a function as distance and time. It is a random variable, and hence we can only speak about a probability, that the probability we can first say that this is the median value PL, 50% of the time it lies above the median, 50% of the time it is lower than the median, and given any value we can characterize what is the probability it takes a value in that region, that is obtained by this, looking at this probability distribution. Further, if you look at it, and this is nothing but the probability that the path loss lies in this neighborhood, this is the probability that path loss lies in, it is the probability that the path loss lies in this region, that is in the small interval, that is the probability that the loss. Hence, now going back, hence x sigma is Gaussian or normally distributed, hence x sigma is Gaussian or normally distributed, right. So, we said x sigma, this deviation is Gaussian or normally distributed. And what is x sigma? X sigma is nothing but deviation about, x sigma is nothing but the deviation about the mean. However, x sigma is in dB, remember x sigma is in dB, hence x sigma is nothing but log 10 of received power, hence x sigma is in dB, which is related logarithmically to the received power. Hence, x sigma which is in dB is related logarithmically this is related logarithmically to the received signal power. Hence, this is also termed as a log normal distribution. It is normally distributed and logarithmically, since it is in dB, it is logarithmically related to the signal power. Hence, this is also termed as a log normal distribution. Hence, this is also termed, hence this is also, this has a log normal distribution. Hence, this has a log normal distribution. This, that is the reason this is also termed as, this shadowing is also termed as log normal shadowing. Hence, this factor, this shadowing factor is also termed as log normal. Hence, this shadowing factor is also termed as a log normal shadowing factor. All right. So, what we are saying is, we are saying that the path loss, that the actual observed path loss is equal to, observed path loss in dB is equal to the path loss, the median path loss plus a log normal shadowing factor. So, this is the observed path loss, this is the median path loss, and this is a log normal shadowing factor this is the log normal shadowing factor, and this log normal shadowing is arising, remember we said, because of the clutter environment, because you might, the user might be behind a wall or a building, which essentially causes additional deviation. So, if you model all such random factors that are arising, you will essentially observe that the received signal strength looks like a random variable, it has a certain mean, which is what we computed using the Okumura model, and then a deviation about this mean. That is what essentially is observed. And now, let us go back again to look at this distribution we had of the path loss. If we look at the distribution, now what we can talk about is, we can talk about is that this is the 50th percentile path loss. Now, what we can talk about is, we can talk about the path loss being greater than a certain threshold gamma. This is, let us say, a threshold and the path loss greater than this threshold gamma is nothing but the area under this curve, that is the probability that the path loss is greater than this threshold gamma is nothing but the Gaussian tail probability. This is nothing but the Gaussian tail probability, that is the probability that this path loss is greater than gamma, and this probability is essentially given as the Gaussian Q function. This is nothing but Q of gamma. This path loss is nothing, this is essentially nothing but, this is essentially nothing, this is given, the Gaussian tail probability is given by the Gaussian Q function. So, this path loss probability is given by the Gaussian Q function. Let us specifically compute how this probability looks like. Let us compute the probability that the path loss is greater than this threshold gamma. Compute. So, our problem is as follows: compute the probability that path loss is greater than compute the probability that the path loss is greater than this threshold gamma, that is nothing but the probability path loss is greater than gamma, which is essentially the probability path loss, remember, is nothing but 50th percentile path loss plus x sigma is greater than gamma, which is essentially the probability that implies x sigma is greater than gamma minus the 50th percentile path loss. And remember, x sigma is a Gaussian random variable with standard deviation or with deviation sigma variance sigma square. Hence, this probability that x sigma is greater than gamma minus PL 50 is nothing but q of gamma minus PL 50 divided by sigma. This is the net probability that path loss is greater than the threshold gamma. Alright, so this is the probability that the path loss is greater than the threshold gamma, because the path loss is a random variable due to the random clutter environment. So, we will stop this lecture at this point and we will continue from here in the next lecture. Thank you.